Here's a problem that I encountered in the Life in Math podcast, which had a very enjoyable geometric algebra series. This one is from Geometric Algebra Lesson 4, Version 2, which is the inner and outer product of dual. Try to. So the proposition was that, let's get my highlighter out here, was that if B is a k-blade, that means that it is the product of k vectors, each orthogonal, but not necessarily orthonormal. If you make some transformation to some other basis, then the resulting basis can be expressed as some constant times all the in-sequence set of basis vectors for each of the k-blades in the alternate basis. So I'm going to go about and try to show that this is the case. We'll start with just an example to get a feel for things. All right. So as an example, let's take B equals A1, A2, and we'll let A1 equals E1, the standard basis element, plus E2, and A2 is E1 minus. Where is my undo? There. E1 minus E2. Now, these are orthogonal vectors. Well, if we take the dot product of A1 with A2, we get E1 plus E2 dotted with E1 minus E2, which is E1 dotted with E1 is 1, plus E2 dotted with E1, which is 0, plus E1 dotted with minus E2, which is 0, plus E2 dotted with minus E2, which is 1, so we have 0. So this is a valid set of orthogonal vectors, not orthonormal, because the norm for each of these is 2. So A1 squared is 2 in each case. So what happens when we make this substitution? Let's see. So we have E1 plus E2 times E1 minus E2. So we have E1 times E1 plus E2 times E1 plus minus E2, E2, and where is my other term? E1, E2, there it is. E1 is 1, and E2, E2 is 1, so minus 1 minus 1. So we have 1 plus E2, E1, minus 1 plus E1, E2. And there's another error here. This should be minus. That's minus. And we're left with 2 E2, E1. Or if you prefer, minus 2 E1, E2. So as a simple example, what we should see is that because of the orthonormality, all of the scalar terms should drop out. And that's exactly what we found here. We're left with just a two-blade. And in this case, we found that the constant in this particular example was minus 2. So now let's try this with something more abstract, but less abstract than the final problem. So we'll just try the two-blade problem, two-blade version of this. So we'll say it A1 as some linear transformation, T1k ek, or ak, say, the not as sloppy here. And here I have implied sum. We can add the sums in to be explicit. So this is, oh, and I shouldn't use k because k is our, I can use k in this case because I'm being restricting the problem to a two-blade. So there we go. And so we can say that A2 is a sum from k equals 1 to 2 of T2k. So we have linear transformation applying to each vector. And what do we get when we write B? So we have B equals A1, A2. So now, before we just go and plug this in, which is what initially questioned the sketch that was on the Life and Math podcast, is let's rewrite this first as A1 wedge A2 explicitly. Because B is a two-blade, then all of the dot product terms between the vectors A1, A2 are 0, and this is a valid transformation to make. Once we make that transformation, now we can plug in our linear transformation, and we get and wedge that with, let's pick a different index variable. Oops. So we'll take a j and a j tilde. So now if we expand the sum out, then we have sum of this over all of kj, kj ranging from 1 to 2. I'll just leave that implicit, of t1k, t2j, ak tilde wedged with a j tilde. And because of the wedge product, we only have to sum over those k's and j's that are not equal. So we can rewrite this as sum over k not equal j of t1k, t2j, ak tilde, aj tilde. And I've dropped the wedge products now because the k is now not equal to j explicitly in the sum range, and we're almost there for this particular reduced version of the problem. So the only thing that we really have left to do is figure out what this constant is. And so we have sum over all the kj terms that are really, we have a permutation of all the kj indices. So it may or may not be clear, but what we really have here is sum over k not equal to j of t1 k t2 j times the sign of the permutation of all the indices of kj times a1 tilde, a2 tilde. So here is our constant. And so now if we want to do this in the more general case, all we really have to do is plug in additional linear transformation terms. We could write that out. So now let's go to the b equals a1, a2, ak case, and we'll write aj equals tj jkl. L is an ugly variable to use with implied sum, or make the sum explicit. Sum over L equals 1, 2. Okay, there's our linear transformation. In the general case, if we plug this all in, we'll do the same thing as we did before. So we'll write B as A1 wedge A2 wedged with AK. So we have the sum over, and let's write K1, K2 to KK, all the indices K1 to KK, which is a mouthful. So we have T1, K1, T2, K2, T, K, 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 times the wedge product of AK1 tilde AK2 tilde AK tilde. And having done the two-dimensional two-blade problem, how to do this in the K-blade case is pretty clear. And so we can say that this is really the sum over all the K1 not equal K2 not equal KK with the same term times AK1 tilde AK2 tilde and so forth, AK tilde. And we will get almost the same result. And the end result is that B equals alpha A1 tilde AK tilde, where alpha is the sum over all the K1 not equal to K2 not equal to KK of T1, K1, T2, K2, T, K, K, K. Uh-oh, we have the KKK in there. This became a Southern racist math problem without my realizing it. And all of that times the sign of the permutation of K1, K2, KK. So there's the end result, if I have things correct. And kind of a fun little problem. It was fun to work through it. And that's it for today.